Hello, this is Mr. Melo here, your online math teacher, and welcome to my channel. Today we're going to be continuing my series on analyzing functions from a pre-calculus perspective. So if you find this video helpful, please consider smashing the like button, subscribing, and checking out my other videos. So let's get to it. And today we're going to be talking about the notion of concavity. And it might be a fancy word that you've seen or not seen before, but it's not that bad of a concept. So let's ask ourselves first, what is concavity? And here is a definition for concave up. So a function is concave up if its rate of change is increasing. And you might remember the term rate of change from an algebra class when you talked about slopes. And we can have two situations that are considered concave up. You could have a graph that is increasing in concave up, or you could have a graph that is decreasing in concave up. And as I wrote in my note here, imagine if we shrink ourselves down and walk along this function in the positive direction. And I reference secant lines here. So in particular, we are going to walk on the following secant lines. So you see me walking along these lines here. As I'm walking, the steepness of these lines, the slope of the lines gets even greater. So maybe I start out, this slope is somewhere around a half. Then it becomes 1, then 3 halves. So I see it's increasing. In the other picture, which is a little bit more complicated, is the slopes are still increasing because these are all negative slopes. And as the negative slopes get less steep as I'm going down this hill, because I'm walking in this direction, we are seeing that the slopes are getting closer and closer to becoming positive. So the numbers are getting bigger. So that's what I mean by the rate of change is increasing. And concave down is the exact opposite of that. And that's when the rate of change of a function is decreasing. And again, we can have two pictures here. We can be increasing and concave down, so something like this, or we can be decreasing and concave down, so a picture like this. And again, we can think about what would happen if we were walking along secant lines on this function in the positive direction. If the slopes decrease, then we're concave down. So you can see in these pictures, as I'm walking along, the slopes of these secant lines is decreasing. Maybe it starts out at 3 halves, then goes to 1, then goes to 1 half. Similarly, as I'm walking along on my other picture, the slopes are getting steeper because they're getting more and more negative. And more negative means it's decreasing. Maybe we started out at negative a half, then went to negative 1, then went to negative 3 halves. So we still see that the rate of change is decreasing in both these pictures. Now, the question is, how are you going to apply this in an actual problem? And you'll usually be given a graph like this on the right. And remember, increasing and decreasing is similar. You can think of a little me walking on the graph in the positive direction. And when I'm walking downhill, it's decreasing. And when I'm walking uphill, it's increasing. So when you do that, you get the following intervals are where you're increasing and decreasing. So from negative 5 to negative 1, and then again from 3.5 towards infinity, I'm always walking uphill, walking downhill from negative infinity to negative 5, and again from negative 1 to 3.5. But then I can bring in that cupping type thing. Is it concave up or down? And when you do that, you want to ask yourself, where do you think the points are where you're going from being concave up to concave down, or vice versa? Where is there a change? And those changes we can see in this picture are located approximately here at about -3, -3. So -3, -3. Then roughly again right around 2, -5. And that's about it. So it looks like we're going to be concave up over on the left. Then we go to concave down for a while before we go concave up once again. So if you need to answer a question about concavity, you're going to say that we're concave up on the intervals from -infinity to -3, and again from 2 to infinity. And then where we're not concave up here, that's where we're concave down. So from -3 up to 2. And you notice I'm not including the values of these points when I'm deciding the concavity. So, because it's not clear, do I throw it in the concave up or concave down portion? So I just don't include them. And the names of these points where we change concavity, these are called inflection points. So those points that you started out by identifying are where concavity changes. And the best you're going to be able to do is estimating them right now based on a picture you see on a graph. Typically, to be able to find these points with algebra and exactly, you're going to need calculus, which we don't quite have yet in precalculus. So, and as just like with increasing and decreasing, you describe where you're concave up and concave down by the intervals on the x-axis. So you're not talking about the y values with concavity here. So, my tips about concavity: know that the points where the graph changes concavity are called inflection points. You should know that terminology. Look at the graph of a function to answer questions of it, because you need calculus to do it algebraically. When you're describing your concavity, just do it with intervals on the x-axis, just like increasing and decreasing. And when you're thinking about concavity, think about if you had a bowl in front of you. And if part of the graph looks like the bowl is set right side up, then it is concave up. So here's my little bowl here. And if it looks like part of the graph is a bowl that's being set upside down, then it's concave down. So I hope you found this video useful. If you did, hit the like button, check out my other videos, and have an awesome day.